Hello, and welcome to a brief introduction of NMR, the Carbon NMR edition. What will make this presentation unique is, first of all, the focus on carbon NMR first instead of just hydrogen NMR. And also, we're not going to talk about the theory. So if you wanted to know more about magnetism and spin states, that's not the focus today. The focus today is going to be using it to solve organic type problems. So the first thing that I want to address is that NMR has lots of different values that you might want to use. So you want to make sure you know if you're going to have those available or if you're going to have to memorize those. For my class, we're definitely going to use a handout. So the handout that will be given is shown on the right, and you'll be able to find that on Blackboard. So you won't have to memorize all the stuff. If you look on the top, you can see that that's going to be hydrogen NMR. We'll figure that out later. And then on the bottom is the carbon NMR. That's the part we're going to focus on today. So since we're going to talk about some problems, you might want to have this handout available, so you might want to go ahead and print that off if you haven't already. All right, so let's get started talking about the NMR basics. I'm going to start assuming you don't know anything about hydrogen NMR either, so we're just going to start from scratch. All right, so the first thing you want to know from a practical standpoint is what are we going to use the information from the NMR for? Basically, it's going to be used to determine organic structures. So carbon NMR can be used a little bit for this, and then hydrogen NMR even more so. You can actually figure out the structure from just the hydrogen NMR. But we'll talk about that later. For now, the first thing that I want to look at on the NMR is the number of peaks. Finding the number of peaks is very easy. You just look at the spectra and count them. Both carbon and hydrogen NMR have a certain number of peaks, and knowing how many peaks it forms is going to be important information for figuring out the structure. The next thing that we will look at is called the shift. The shift is going to be something that you can also see, but it's going to involve the numbers at the bottom. So you're going to see where the peak is left to right on the scale, and you're going to use that number and match it to the handout. And once you match it to the handout, that's going to give you an idea about the functional group. Now for carbon NMR, that's pretty much all the information you're going to have, but there's a couple other things you can learn from hydrogen NMR, so I've shown these here at the bottom, just so you know for future reference. So now that we've got them all listed, let's start talking about what these things mean. All right, so as you can see here, I've got some spectra. The top one is a carbon NMR spectra. So as you can see, it just has straight lines, and those are the peaks. They come up from the bottom, and that's sort of what they look like. If you look at the bottom, there's an H-NMR. The peaks look a little bit different. They're a little bit wider, and they also have this like jaggedy thing going on. So that thing at the bottom is called splitting. So hydrogen NMR has splitting peaks. Carbon doesn't have that. They're all just single peaks that go straight up and down. They tend to be very, very narrow. All right, so when you count them, you just have to keep that in mind. So for the carbon NMR at the top, you can see it says this spectrum has 2 peaks. So where do you see the peaks? Right, so there's one over here on the left, and then there's one over here on the right. That's the 2 peaks. For the hydrogen NMR, there's 3 peaks. So where are some peaks on there? Right, so there's a peak here sort of by 3.5. There's also a peak over here at like 1.1-ish. And then the other peak, do you see it? Is this really small peak on the left, so it's kind of fatter than the other one, but it doesn't look symmetrical, and that's how I know that's another peak. We'll talk more about that when we talk about hydrogen NMR. But so this NMR has 1, 2, 3 peaks. So that's great. We know how to count the things, even if they're splitting. But what does this information actually mean to us? Basically, what it means is that every peak that we have is a unique carbon or hydrogen, depending on which type of NMR you're looking at. So the carbon NMR at the top has 2 unique kinds of carbon, and the one on the bottom has 3 unique kinds of hydrogens. So when we say unique, we mean they're in a different environment. So being in a different environment for an atom is a little bit different than us, right? So it just means what other atoms are nearby. Is there an electronegative atom like nitrogen nearby, or is it maybe 2 carbons away or 3 carbons away? That's going to make a difference to these different carbons. What it's going to mean for our structures is that we're going to be able to tell if there's symmetry in the molecule or not. So let's look at the first example with the carbon NMR. As you can see, I've drawn the structure of what this actually is. This is called acetone. It's a type of ketone. And this molecule has some symmetry so that 2 of the carbons are considered the same. So looking at the structure, which of the 2 carbons do you think would be similar? Meaning they're connected to all the same atoms. Right, so it's going to be here, if I call this carbon 1, the other carbon that's the same is going to be on the other side. That's also going to be 1 because there's a plane of symmetry down the middle. Then in the middle, there's one more carbon, so that'd be carbon 2. So those are the two different carbons we see on the NMR. Now that's all we can get from the number of peaks, but right now we still don't know which peak is coming from which carbon signal. So we're going to work on that next, but first let's do a few more examples that might have symmetry. All right, so let's look at these other examples. So as we said, the first example is the one we just saw, that's acetone. So whenever I'm counting peaks, I'm going to just number them until I come to a place where it seems like there's a plane of symmetry, all right? So, and we're only counting carbons, keep that in mind. If it's carbon NMR, we're not going to see oxygens or nitrogens on that NMR. It's only carbons that react this way. All right, so for the first one we said it's going to be 1, 2, and then that's the same as the other one, right? Because there's a plane of symmetry in the middle. So that would only have 2 peaks. So what do we think about the next structure below acetone? That's a little bit harder, right? Take a minute to pause the video and count how many carbons you think you see. All right, so did you get at least 6? Hopefully you did. So here's what it looks like. So each of these is a unique carbon. Even though 3 and 4 are both by an oxygen, they have something different on the other side, so it doesn't pass the symmetry test. If I put a plane of symmetry down the middle, this side looks different because it's got that extra carbon than this side, so I can't put a plane of symmetry there. So if I have this 3, it's attached to a carbon like this, a carbon that's just a CH, and then a CH2. But this carbon's a CH2 that's attached to another CH2, which is slightly different, and then that 6 would be kind of the same. All right, so that's why they're still technically different. This is really sensitive. Now, why did I not number this one? What does this one match? Right, this matches 1, so we can make a plane of symmetry here at this carbon. It doesn't go through the entire molecule, but it doesn't have to. I know that this carbon 1 is always attached to carbon 2, just like this carbon 1 is always attached to carbon 2, and then the chain continues. So it's connected to the exact same thing for the whole rest of the chain, and that's what makes it symmetrical and equivalent is what they call it. So for this molecule, we should have 6 peaks. All right, so let's look at the last one on the bottom. Count how many peaks you think we'll have there. Is this what you got? All right, so there's only 2 carbons in that molecule, and they're both different, right? So then there should only be 2 peaks. So good, hopefully that worked out. If not, be sure to ask me some questions. Now let's move on to something a little bit more complicated called shift. All right, so we mentioned before that we can use the shift to figure out some information, and we're going to use the handout from Blackboard. But what it actually shows us is what functional group the carbon is either in or nearby. So if we can use that handout, we'll be able to see like what the possibilities are. All right, so the reason this works has to do with something called shielding. So before we can talk about that, we need to go back for just a minute and talk about what NMR is. So NMR stands for nuclear magnetic resonance. So what we're looking at in the molecule is the nucleus of certain atoms. In this case, we're looking at carbon nuclei. So whenever we're looking at that and we're trying to basically make something happen to the nucleus, electrons would actually get in our way. So if you think about all of the atoms have an electron cloud around the center, right? So if something can pull those electrons out of our way, it's called de-shielded. But if they're just there hanging out, blocking our path to like get energy in there, then that's called shielding. It's like protecting them. So shielded atoms have some sort of weak electron donating group. So if you look here on the right, these are atoms that are more shielded. So if I have a carbon that has a lot of hydrogens or a carbon that has R, this R in this case would be like alkyl groups, so like more carbons, okay? So in this case, R equals alkyl group. Okay, so then how can we de-shield the atoms so that we can have an easier time getting the energy in there? So there's some examples at the bottom. So there's a couple ways you can do that. So one way is obviously to have an electronegative atom, and that's going to pull electrons away. So if I look at this one here, you can see the oxygen, that's going to be a polar bond. So that's going to have a dipole and pull electrons towards the oxygen, which pulls them away from the carbon and leaves the nucleus a little bit more exposed, okay? Another option is I can have an electron withdrawing group. So that would be like if I have a positive or a partial positive, that's going to pull electrons away. Halogens are really good at this. Actually, like a carbocation would pull electrons away from a neighbor. So those are some examples of electron withdrawing groups. And then the last option is for carbons, if it's sp2 or sp hybridized, that's actually taking electrons away from the middle because you have less s character, and s, remember, is a sphere, which is like sort of around the middle. But a p orbital is like a dumbbell, and if you look at the dumbbell shape, there's no electrons in the middle of that. So that means at least 2 of the electrons can't be in the middle now, and that's actually a good thing for the NMR. So it makes it easier to get to, and therefore it's going to be further to the left, which we'll see. So just to be clear, let's look at the molecules on the right and figure out which one of these things would have these effects. So electronegative atom, the carbons that are next to electronegative atoms, so we'll do in this color, are going to be this one, and that's all, right? That's the only one that it's more electronegative than carbon. All right, electron withdrawing groups. So things that are next to something that's withdrawing. So either they're next to a positive, they're next to a partial positive, or they are next to like a halogen or something, okay? So the only one I see is actually this one here because it's next to a double bond O, which actually has a partial positive. So that's an electron withdrawing group, okay? And then the last one is sp2 hybridized. We don't have any sp for this time, just sp2. So which ones are sp2 hybridized? Right, so it'd be this one again. This one's got a lot of stuff going on. It'd be all of these carbons on the benzene ring, and then it would be these two on the alkenes. So those should all be things that you see further to the left. And the more effects you have, the further left it should be. So let's see what that looks like. All right, so generally speaking, when we look at the spectrum, we're going to see the whole thing, right? We're going to read it from left to right because left has the more electronegative and deshielding things. Those are actually the more important functional groups. Most people aren't worried about the functional group of an alkane, which is very shielded, right? So we want to focus on the left. So if we go from left to right, it also will help you eliminate a lot of things, especially when you're doing hydrogen NMR. Now, carbon NMR has a little bit more overlap, so we'll usually have choices for that. So we'll talk about that strategy in a minute. Okay, so if we look here, we have two different functional groups. We're going to take these numbers and then we're going to look them up on the chart. So if we look over here, we have one that's about less than 210, right? Because that'd be 210. So it's about like 207, we'll say. And then we've got one down here that's about 32-ish. And the units is always going to be parts per million. That's just the units that they have, all right? So parts per million. All right, so we're going to take those and just look up on the chart. Okay, so let's look at that. All right, so here's my handout. Like I said, I'm going to focus on the bottom part because I'm doing carbon NMR, so let's do that. All right, so let's look at the numbers where it says about 207. So if we look here, there's the 200, there's the 220. It's kind of hard to see probably, but right there is one of our peaks. And then right around 32, this is 20, this is 40, so 32-ish, be right around here. So if we look on the left, that's pretty easy. It's got a carbon double bond O with either an R group or a carbon double bond O with a hydrogen. They just are abbreviating and trying to put them together. So this means it's either going to be a ketone or an aldehyde. That's what that means, okay? And then if we look over here, basically there's lots of things. There's just regular carbons attached to carbons. That's these guys. There's things attached to OHs and NHs and halogens. The thing it doesn't show is there's also things that are attached to a double bond, but like next to it, so like this. So that's another option that we could have. So generally, this is the thing that could be in the same range. And that's actually what this one is. If it's got a double bond O, it probably has something next to the double bond O, so that's what that one's going to be. Okay, so let's look at the structure. So here are the two peaks, and then we can't really identify it just from the peaks, right? It was too vague on the right side. But we do know that we have a ketone, and we know we have at least 2 carbons. So if we have some choices, it would look like this. It's just this molecule again, right? It's the acetone. So if we look, peak B is the one that's really far over here. That's B. That's the carbonyl carbon. And then A is going to be the one that's next to a carbonyl, so it's slightly downfield.